In this episode, we dive into two exciting frontiers of AI research: how to distill a transformer into a pure Mamba model without losing its strengths, and how to fine-tune reasoning models with synthetic data that truly matches the student's style. One paper reveals a clever two-stage recipe for cross-architecture distillation. The other proposes a teacher-student collaboration framework that preserves reasoning quality while avoiding distribution mismatch. Together, they point to a bigger question: how can we transfer intelligence more effectively across models and training setups? Let's explore the first paper. Attention to Mamba, a recipe for cross-architecture distillation. Attention to Mamba proposes a two-stage cross-architecture distillation recipe that transfers a pre-trained transformer into a pure Mamba-style student without hybrid attention blocks. Using Pythia as teacher and open web text for distillation, the method first distills softmax attention into hedgehog-style linear attention via a learned feature map. Yx equals sigma wx plus b, trained by cosine matching, then uses that linearized attention as a principled initialization for an adapted Mamba block. The second stage copies the hedgehog-derived Q, K, V behavior into Mamba's SSM parameters, freezes them to identity-like settings at initialization, then fine-tunes the full block with cross-entropy while enabling Mamba's gate and convolution branches. The key novelty is architectural alignment through initialization rather than direct transformer-to-Mamba matching, which prior work found unstable. The resulting hedge Mamba layer preserves Pythia 1B behavior much more closely than naive distillation and outperforms a hedgehog-only baseline. On 1B models, perplexity is 14.1 versus 13.86 for the teacher and 14.89 for hedgehog. Downstream scores also improve, including ArcEasy 53.66 versus 52.74, PyQA 68.72 versus 68.01, BullQ 55.20 versus 54.80, and HelloSwag 41.87 versus 40.79. Ablations show the MambaGate branch contributes the largest gain, reducing perplexity from 14.58 to 14.11 when added on top of SSM plus conv. A token allocation sweep over 10B distillation tokens shows that allocating 10% to stage 1 and 90% to stage 2 is best. Either stage alone degrades sharply, with 100 over 0 reaching PPL 25.71 and 0 over 100 reaching 17.08. Scaling from 1B to 10B tokens improves results monotonically, confirming the recipe benefits from more second-stage fine-tuning. Let's explore the second paper: how to fine-tune a reasoning model. A. Teacher-student cooperation framework. 2. Synthesize student-consistent SFT data. This paper shows that naively fine-tuning a reasoning model with teacher-only synthetic SFT data can hurt performance because the teacher's output style is distributionally mismatched to the student. The authors formalize SFT as learning both capability tokens and style tokens, then argue that reasoning quality is driven mainly by capability tokens, while style mismatch induces harmful loss. Their solution, TESSI, is a teacher-student cooperation synthesis framework that alternates token span generation between a strong teacher and the student. The teacher generates capability spans, the student generates stylistic spans, and a generate then rollback boundary predictor truncates each raw span to the correct token type. Boundary models are trained as token-level sequence labelers on 100K annotated reasoning segments using Qwen 306B base for efficiency. The final answer is generated by the student to preserve consistency. On code reasoning, using GPT-OSS120B to supervise Qwen 3, 8B with teacher-only SFT drops performance by 3.25% on Live Code Bench Pro and 10.02% on OJ Bench, whereas TESSI boosts Qwen 3, 8B, by 11.25% and 6.68% on those benchmarks. In the main table, TESSI reaches 36.69 on Live Code Bench Pro and 25.43 on OJ Bench versus 22.10 and 18.75 for the base Qwen 3.8B, and it also improves AIME 2024 by 3.75% and AIME 2025 by 0.93%. The method generalizes to Qwen 330B, A3B, DeepSeek, R1, and Qwen 3235B, A22B. Thinking as teachers, with consistent gains over teacher only, An analysis using TF-IDF-PCA shows TESI shifts synthetic data toward the student distribution while still retaining teacher-level reasoning quality. It also reduces average output length by thousands of tokens relative to teacher only. That's a wrap on today's AI paper highlights. Thanks for watching.